In this video, we will begin Chapter 8, which is all over the principle of inclusion and exclusion. We will first explore the topic of the principle of inclusion and exclusion in this video, Section 8.1. In the subsequent videos, we will go into a little more specifics for exactly, at least, or when nothing is in the right place. So our overall goal is essentially to find the number of elements in the union of any sets, disjoint or not. And so when we're talking about the union, we're really talking about this section and this section and this section. That is all the union. So notice in this one, we have a part that is overlapping. This is called the intersection. And so obviously these sets are not disjoint. If they were disjoint, we would be looking at two circles and that were not connected. And that would be really easy to find the number of elements because we would just take whatever's in A and whatever's in B and add them together. So the fact that we have an intersection here makes it a little bit more complicated. If we have three sets, A, B, and C, again, we would be looking at the entire region of any elements that fell into A, B, or C. So let's take a look at a fairly straightforward and simple example. And I just want to point out to you that typically when I draw a Venn diagram, this box is the universe. So in this case, if we're talking about people who are attending a play, the universe may be all the people who attended the play. And then within it, we're looking at people who are from Omaha, people who are men, specifically men from Omaha. So based on the universe that we're talking about, people who attended the play, these would be women not from Omaha, essentially is how that would work in that universe of everybody who attended the play. So keep in mind that the box would include all of the people who attended the play, and we're not going to deal a lot with what's in the box now. We're going to deal with all of the stuff that is within the union of sets. So let's take a look. Suppose we have a group of people attending a play. 34 are from Omaha, 24 are men, and 18 are men from Omaha. So typically what I do is if they give me a number like this, where I can put it directly onto my Venn diagram, that's what I'm going to do. 18 are men from Omaha. Then it says 34 are from Omaha, but notice that within the Omaha circle, I already have 18. So I have to take 34 minus 18 to come up with that 16. So I've got 18 in the middle, I have 16 on the left, and notice that these two together add up to that 34. And then the same thing with men. We know 24 total are men, but we already have 18, so we're going to take 24 minus 18 to get 6 that are just men. And of course this would mean men that aren't from Omaha. This would mean women from Omaha. And then of course we don't know this number out here, and we really don't care right now. I do want to point out the notation that you'll see quite often, and that is the two straight lines looks like the absolute value. So essentially what we're asking here is to find A union B, which would be find the number of elements in the set of A union B. So we would take 16 plus 18 plus 6. That would be everybody here, and everybody here. So we end up with 40 total. Now obviously creating a Venn diagram for our last example was pretty easy because we only had two sets, but what we want to do, what we're working toward, is to get to the point where we don't have to make a Venn diagram, because we might have 4 sets or 5 sets or 6 sets, and that would just be a lot of drawing for nothing. So let's use the general addition rule that you've learned long ago that says A union B, or the number of elements, the cardinality of A union B, is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. So again, let's take a look at that exact same example. Instead of having to do the subtraction here to get 16 and do the subtraction here to get 6, I'm just going to use the numbers directly from my question. 34 are Omaha, 24 are men, 18 are men from Omaha. Notice here I'm taking the number of elements in A, which is people from Omaha, plus the number of elements in B, which is the people who are men. I'm subtracting men from Omaha, and I get, that should be an equal sign, I get 40, just like I had on my last slide. So the question is, why does this work? Well, it works because when I'm finding, let's get rid of some of these colors, when I'm finding the number of elements in A, that's all of this. That's 34. When I'm finding the number of elements of B, which is men, that's all of this, which is the 24. And then what I'm doing is I'm subtracting this region, because as you can see, it's both blue and green, which means I've counted it twice. So what I have to do is subtract it once so that it works out to the 40 that I'm looking for. So here's a question for you to try on your own using that same principle. Again, I've made it very straightforward. You can certainly feel free to draw a Venn diagram if you'd like, or just use the principle of inclusion and exclusion to add and subtract to find the number. Our goal is to find the number of students in the class, which would be A union B. So when you are ready, press play to see how you did. So again, I would start by taking a look at the fact that we have 25 who are in computer science as a major. So the cardinality of A is 25 if I let A equal computer science. And then I would look at mathematics as a major is 13. So the cardinality of B is 13. The number of students majoring in both is 8. So essentially they have told me that A intersect B, the number in each, or in both, excuse me, is 8. So now, without even having to do this, which of course I can do that if I want to, but really all I have to do is take 25 plus 13 minus 8 to get the 30. And that would be the same thing if I drew the Venn diagram out to determine the total number, but what I want to get away from is having to have that Venn diagram. So really what we'd like to do is to be able to generalize for however many sets that we have. So we've really only focused on 2 sets. So let's take a look at 3 sets and then see if we can start to generalize so that we don't have to create a Venn for 4 sets, 5 sets, 6 sets, etc. So if we look at 3 sets, what we're looking at is A union B union C, which I don't have colored in. I only have some intersections colored in, which we'll talk about in a moment. But we're going to look at an example with 3 sets, and I want you to know that we obviously have written this A, B, and C. This would be the same as if I said A1, A2, A3, just by changing this to A2 and changing this to A3. So you might see it with a lot of A's instead of A, B, and C. I also want you to note that if an element belongs to either A or B and C, so I'm saying A union B intersect C, that's the part that I have marked in pink here, then it belongs to either A intersect C, which is this section, or B intersect C, which is this section. So the reason I point that out is we're going to use that when we're coming up with our generalization. So what I want to do now is I want to start with trying to generalize what's going to happen when I'm trying to find the cardinality of the union of a different number of sets. So we've only looked at 2, this is with 3, and I'm going to do a lot of substitution using either 1, which is my general addition rule, or 2, which is that thing that we just talked about that said if we've got some element that's in the intersection of A union B and C, then it's either in the intersection of A and C or B and C. So what I'm going to do is just a lot of substitution, rearranging, etc. It's not important that you are able to do this yourself. I didn't want to just give you the principle of inclusion and exclusion without any explanation as to where it came from. So just try to pay attention. Don't worry about taking great notes because you're not going to be asked to do this yourself. So I'm starting by saying I'm trying to find A union B union C, the cardinality of that union. So all I did was rearrange, which is perfectly acceptable. And now I'm going to rewrite using number 1, which is the general addition rule. Remember, the general addition rule says if you're taking the union of two sets, which is exactly what I'm doing here, union of two sets, then I'm going to take the number of elements in the first set plus the number of elements in the second set minus the intersection, which is exactly what I've done. I just have 3 sets instead of 2, but it doesn't change anything. Then I'm going to take, and I tried to color code for you, so hopefully that helped, A union B. Again, I used number 1. And then this guy, I used number 2 to rewrite. So I'm just applying those principles. I had the union of the intersection of 2 sets. Now I'm just going to rearrange because I want any of these single sets sort of together. So I've really just kind of moved the C over, and that's it. Everything else stayed the same. Now I'm going to rewrite again. So again, everything here, if you'll notice, stayed the same. Only my green guy got rewritten. Now I'm going to rearrange again because here I have 2 sets together. So now I've got 2 sets, 2 sets, 2 sets, and then something a little bit more complicated. So obviously I'm going to work on this complication next. And that complication is essentially saying if I have the intersection of A and C with the intersection of B and C, then I'm really finding the intersection of A and B and C. So if you'll notice what I've done before we get to the end here is I have all of my sets of 1 minus a set of 2, minus a set of 2, minus a set of 2, plus a set of 3. Now, you can leave it just like this, or you can group them to say, I've got all of these, I'm subtracting all of the sets of 2, I'm adding all of the sets of 3. These two things are exactly the same, and this is essentially the principle of inclusion and exclusion. So again, just to make clear the pattern that we found, with 2 elements, I had my sets of 1 minus a set of 2. With 3 elements, I had my sets of 1 minus the sets of 2 plus the sets of 3. And so we can see if we moved on to 4 elements, I would probably then be subtracting all of the sets of 4. And that pattern would continue. Add the sets of 5, subtract the sets of 6, etc. So to this point, we've really just looked at sets. Now I want to look at conditions, C1, C2, etc., which is really the same thing as what we just looked at. The notation's just a little different. So I'm just changing the notation, but I'm doing the exact same thing as before. Again, I'm looking at the universe, which we're calling N. We're saying this is condition 1, which in our last example could have been men or people from Omaha. I don't remember which one. The other condition would be men or people from Omaha, whichever the other one was. This means it meets people who meet both conditions, or elements that meet both conditions. And then I want you to notice the notation here, which we haven't really talked about yet, which is not C1, not C2. So again, when we were looking at that example, we were looking at women not from Omaha. So not men, not from Omaha. You get the idea. So again, if we're looking at our principle of inclusion and exclusion, if we're using that new notation, it just looks like this instead. So if I wanted to find this number on the outside, not C1, not C2, how am I going to do that? So if I'm trying to find this region, it makes sense that I would just take n, which is everything inside of the rectangle, and I want to subtract everything that's white, which before we looked at as A union B. But of course now we're changing up our elements, so instead of saying A union B, we're saying, just like we talked about on the last slide, we're looking at subtracting number in C1 plus the number in C2 and adding the number in C3, or sorry, number in C1, C2. So subtract, add, etc. So again, I can write it in this way, or by distributing that negative, this is what you're going to get to. So again, looking at a pattern, we're saying take the number of elements in the entire universe, subtract any that are just one set, C1, C2, add any that are in two sets, then I would subtract any in three sets, add any in four sets, etc. So let's take a look at this first example together. Notice they're going to give me some information, and I want to kind of take you through step by step the order in which you might do this. So it says out of a sample of 2,500 students. So this to me says that is the universe. I'm starting with 2,500 students. They tell me 1,232 have taken a course in Spanish. So I'm going to let C1 be people who have taken Spanish. Then of course NC1 would be 1,232. And I'm going to repeat that for French, which I'm going to call C2, and Russian, which I'm going to call C3. And then of course assign NC3 to be 114 and NC2 to be 879. Then it gives me information about people who are enrolled in two classes. So 103 in Spanish and French, that would be N. So again, this is our first step, is to say who is what, and then this part I've already really done. But now I'm looking at 103 have taken Spanish and French. Well, Spanish and French are C1, C2. So N C1, C2 is 103. 23 in Spanish and Russian, so that's C1, C3. And then C2, C3 is 14 because 14 have taken French and Russian, and then 7 have taken all three. And the question itself says how many students haven't taken any of the three languages, so that is this. Here's our goal. Now, keep in mind that we already have our blueprint for how to find the number of elements not in C1, not in C2, not in C3, which in our Venn diagram would be the part in the box, but not inside any of the circles. So we are essentially finding this. So I'm taking the number of elements in the whole set, and I'm subtracting the union of the sets. So we're not writing it as a union anymore. But remember that all of this turned into subtracting anything that's in one set, adding anything that's in two sets, subtracting anything that's in three sets, and continuing that pattern. So now all I have to do is plug in the numbers from here. I've got 2,500 minus 1,232 minus 879 minus 114. I'm adding 103, adding 23, adding 14, subtracting 7. Who's left over? 408 students who didn't take any of the languages. Let's look at another example that you will see questions like this quite often. I uncovered most of it to begin with, so you didn't have to write anything down. But this one says, how many integers from 1 to 500 are not even or divisible by 3? So before I even move on to any other information, I'm looking at the fact that I'm saying 1 to 500, which means n must be 500 because there are 500 integers from 1 to 500. Not even, which means even is going to be C1, so not even would be not C1. Divisible by 3 would be C2, and of course we're saying not even or divisible by 3, so I'm really going to be looking for not C2. So again, this is saying C1 is even, C2 is integers divisible by 3. So how do we find those values quickly? Well, we're going to use the floor function. So remember, the ceiling function says round up no matter what to the next integer. The floor function says round down no matter what to the integer below. So if I take 500 divided by 2, I get exactly 250. I didn't have to round that one. If I take 500 divided by 3, and of course I divided by 2 because anything divisible by 2 is even. Divisible by 3, I'm just going to divide by 3. I get 166 and change, which, because it's a floor function, rounds down to 166. And then to find the number that are both even and divisible by 3, notice what I'm going to do is I'm just going to divide it by 6, 2 times 3, which is these two values together. And that's 83, rounded down. Now, to compute not C1, not C2, so the number that's not in either of those sets, remember my goal is to take, or my formula for this is n. I'm subtracting C1, subtracting C2, I'm adding C1, C2. So that's all I have to do. 500 minus, and then again, you can group those if you want to, but you don't have to. I could have just put minus 250 and then minus 166. Either way, I'm subtracting either of those values. Then I'm adding the 83 to get 167. So there are 167 integers that are not even or divisible by 3 in the integers from 1 to 500. So here's one very similar to the one that we just did. I'm asking 2, 3, or 5, so feel free to look back at your other example before doing this one on your own. When you are ready, press play to see how you did. So again, C1 is divisible by 2, C2 is divisible by 3, C3 is divisible by 5. So all I have to do is compute each of those numbers. So here's my elements that are in just one, C1, C2, and C3, by using that floor function again. C1, C2 would be 2 times 3, or 6. C1, C3 would be 2 times 5, or 10. And C2, C3 would be 3 times 5, which is 15. And then, of course, I have to find the number that are in all three. So 2 times 3 times 5 is 30, and I get 16. So now I'm just using my formula or my pattern that says subtract anything with 1, add anything with 2, subtract anything with 3. I get 134. I did want to quickly identify for you sort of a generalization of the principle in case you see this in your text or in other videos that you watch. We already know the pattern, and our pattern says in order to find basically not n, which means not C1, not C2, etc., for any number of conditions that we're dealing with. We're going to start with the universe. We're going to subtract elements with size set 1, or set size of 1, add elements with set size of 2, subtract with set size of 3, etc., which means essentially that I'm taking negative 1 to the t, because that's going to give me the plus, minus, etc., and then however many values that I get. So to write it in a generalized way using summation notation, you might see it written like this, which is really the exact same thing that we've been talking about, so don't get freaked out if you see something like this. We're saying start with the universe, take the sum of all of the sets of size 1 from 1 to however many conditions you have, add sets of size 2, subtract sets of size 3, etc. Or you may also see it written much more simple, which I like, as this, which says S sub 0 is n, our universe. S sub 1 is the sum of all of the sets of size 1. I'm subtracting those. The sum of all the sets of size 2 I'm adding, subtracting sets of size 3, and so on.